So, he is a professor in the Department of Electrical Engineering at IIT Kanpur. So, Professor Behera obtained his BSc and MSc from Regional Engineering College, Rourkela, and then PhD from IIT Delhi. He has been a postdoctoral fellow at the German National Center for Information Technology, and his research interests are mainly in the area of machine learning and intelligent control, cognitive modeling and brain theory, Bayesian networks, visual tracking and eye movement, intelligent robotics, and multi-agent systems.
Professor Ashish Datta, this I am supposed to speak on robotics, which I will do, but half an hour I will take liberty to speak something little different, but connected to robotics as well. Is a cyber physical system, right. So, what is cyber physical system? This is something coming in a big way. Each smart device can be tracked and monitored over internet, wireless, smartphones. We have all kind of gadgets that are there. Things can be connected. I was actually a month back in Mumbai. We had a meeting, and in that meeting, one NRI, he suddenly, there was he has some smart device with him, and some alarm bell rang. So, I said, what is happening? Then he opened the device. I saw there is a house somewhere, appeared to be in foreign countries, and there are two kids standing there. And then he pushed some button, the door opened, and two kids entered inside the house. I said, where it is? He said, this is in my home. Where is your home? New Jersey. So, it is in Mumbai. I said, why you have to do this? Now, my wife is sick, she is inside, so I am doing this. So, you see that things are all connected. Everything with a so called technological advancement, things are all connected. So, smart homes, smart cities, smart grid, intelligent transportation system, IoT based healthcare, social networks, teleoperated robotic systems. Recently, some of my MTech students who are in Abu Dhabi, they were controlling robots in my lab, right. There is a parallel manipulator sitting in Petroleum Institute, and they are sensing the force feedback here, and based on that they are giving the control command, and command is coming over the internet, right. So, McKinsey Global Institute has predicted that IoT will produce a business of the tune to 2.7 trillion to 6.2 trillion dollar. You know that Indian GDP is around $2 trillion, total Indian GDP. Okay. So, but IoT is going to produce 3 times of that. This is a prediction. How much it will be successful, we do not know. Now, let us understand what is IoT or cyber physical system. So, this is a quote from Dr. Mindel. The era of cyberspace and the internet, with its emphasis on the computer as a communication device and as a vehicle for human interaction, connects to a longer history of control systems that generated computers as networked communication devices. So, there are 3 things when we talk about cyber physical system. One is distributed computing. You have clouds, or you have different servers all connected, and or you have small agents distributed, and they all have their own distributed computing platform. Distributed control, every agent has their own control, and then there is some master control over that. So, control, computing, and finally communication, they are all communicating with each other, right. So, when all these 3 they combine, the science of that has not developed, to be frank with you. Okay. So, science of that has not developed. So, if we go a little bit of history, we will see 1950 to 2000, and still it is continuing. First we saw computing platform, the foundation of that started by the ENIAC platform, then von Neumann, the great, he is one of the great founding father of the computing platform, or the computational concept itself, or theory of computation, you can say. Alan Turing, of course. And then once we recognize that machines can actually compute, then we started thinking about sensor, estimation, those technology. And that was based on Fisher and Wiener. That means you have devices, a machine that can compute, and then you add these sensors that is giving you information. Now you have to make out those information, what this information, meaningful information is there. And then we talked about actuation and control, that was brought by Bode. Kalman became a big influence in the control and estimation theory. And we have communication, Shannon, Nyquist. All of you know Nyquist sampling rate, right? Shannon sampling theorem. And then signal processing, okay. And what happened from 2000 onwards, what's happening now? Now we have systems. We want to co-design the systems that operates on convergence of computing, control, and communication, right. So this is the age of system building. I have my friend Saeed Nahavandi. He actually designed an entire airport baggage handling system, and based on that airport I actually designed, the whole. So that means you don't first put an infrastructure and then start designing things. No, now the new concept is co-designing along with the infrastructure and the systems that will be placed in that. The control, communication, coordination, everything has to be co-designed. So nodes that can communicate, control, and computing, large grand reunification of control, communication, and computation, and that has brought in the pedagogical challenge. Okay. What is that pedagogical challenge? That because a new science is coming, science has to be developed, there is digital and analog divide, that has to be, because all devices, mostly engineering devices, are continuous, and the computing platforms are digital, and how do we seamlessly merge these two different space. And then undergraduate education, postgraduate education. Recently we wrote to MHRD, they are giving us around 8 crore rupees to particularly to give pedagogical instructions on this several physical system. So you see that from real time and hybrid system. So your devices are all real time, and what is hybrid? Digital and analog. When they combine, you create a hybrid system. The analysis, you have automata, hybrid automata, there is switching system, there are many concepts now slowly coming up. Okay. So and together, slowly you see that from 70, so I should take this one, I think, yes. So you see that real time computation 1973, it has its own connotation, real time computation. Then in 90s we talked about hybrid system, and after 2006 people started talking about cyber physical system, right. And not going. So just to give you some idea here. So you have cellular system. Imagine all the cars in your highways are being tracked through radar, and radar is giving to the servers, and they are all tracked. So you see that multiple mobile agents here, and they are all networked. So convergence of communication, computation, and control, where you have also what is connecting them is a sensor network, right. So first generation we understood what is analog control, feedback amplifier, frequency domain analysis, Bode, Evans gave you the root locus technology, Nyquist gave you the stability margin, notion of stability margin. Second generation we have digital control, and particularly it was reinforced by the state space design, real time scheduling, optimization. And third generation we have now network control, embedded computer, wireless network or wired network. And so all these things. So you see there is a, in science, from linear system to nonlinear system, estimation, optimal control, like that we have now in hybrid system. When you talk about a cyber physical system, the approach to control of cyber physical system at this moment is hybrid system. Not necessarily it will remain there, things may change. You see, in 2012, in the centennial of IEEE, the proceedings of IEEE, which is the most impacted transaction, that brought out 12 around how many 19 special issues, and in that the first issue of proceedings of IEEE was dedicated to cyber physical system, right. And so that gives you a perspective why cyber physical system. So this is what I told you, that we have created a consortium of IIT Kanpur, Kharagpur, Patna and Indore, and on giving these kind of courses related to cyber physical system. So pedagogical modules has to be developed. Every module, when the participants they attend, they can float on their own a course. So that means they will be trained in the everything about a course module, and they will appear in exam, they will get a certificate, and they are now ready to float a course, right. So these are some of the things that just to give you some idea where this cyber physical system. You see that here this is a warehouse automation again. So this is what we are now doing in Amazon picking challenge. So you will have such robot, many such robots, okay. They take the order, like you go to Amazon, you check out with some some of the products that you want, books, CDs, videos, whatever, and these robots, these multiple robots, they actually get this order, and there has to be a task scheduler. Based on that, the task will be distributed to different robots, and robot goes, this is a mobile robot and the mobile robot manipulator, it goes and searches the box self and puts into the pack, and there will be automatic packaging, and then it goes for the shipping. So, and when you do this, this is called a robot performing cognitive task. That means it recognizes what is the object, you are trying to understand what are the object it has to pick, and then action also, like for example the action that it has to show, my Samrat, who is actually working on the learning motion profile. That means robot by hand is taught how to reach different. Once the robot knows there I have to go, so how to go. Now you no more do exact inverse kinematics, you actually teach it what is the motion profile such that it does not hit and it reaches hit the obstacle around. Just to give you what is this cognitive task, here it is, you will understand this from the examples. How do we teach? I will talk about this a little later also, a little more detail, but this you see that this is called cognitive task. The robot is being taught how to hit the ball, right, and then it's a lot of things there actually, your visual tracking, motion estimation, and extracting motion primitives, movement primitives, and generalize those movement primitives either using a Gaussian network or some kind of neural network, and then you make the robot to hit the ball. So, you see that it does not do well with minimum examples. So, you you teach it more, give him more examples, and now if you do that, so you will see that robot will do a better job. So, we have put the robot, now Raj Samant and others, they are working on making this robot now play tennis. We have already started working on it. So, we are generating examples. I will tell you how this is actually it can be done. Just to give you another example, this this cyber physical system. So, here you see these are all robots, right, mobile robots, and this line shows that they are all communicated, they are linked. They are linked through, this is linked with this through wireless communication, this is linked with this wireless communication. So, there are link here, right. So, this is also communicated to this. So, you see, and the objective is, we have this multi-agent system, they are connected through a communication link, and what they have to do, this is their, this is the leader, and leader is following a randomly moving target, you see, randomly moving target. Okay. So, this is the leader, and this line what you are seeing, that shows that their communication is not broken. We are actually doing, my students are doing research, what will happen suppose this communication link breaks, whether stability will be ensured or not. There are many research issues in this, and estimation, right. So, there are so many issues actually. You have multiple agents tracking one random target, you can have multiple agents tracking multiple targets, or single agent tracking multiple targets. There are varieties of issues, and each of these problems are increasingly more complex, right. Just to give you some example where okay, I can show you first some of these things here. What happened? So, you see here formation, this formation means there are two robots, they are making a formation, this is called leader, this is follower. See, they have a, now it increase the speed, so it will increase, it will turn, this will also turn, all right. So, like that, here Ranjit, my PhD student, he is about to submit now, he has done a lot of work in many robots, 2 robot, 3 robot, 4 robot, so, and developing different algorithm for making sure that this this system the formation is maintained. Like for example, here also you see this is the leader, this is the follower, and there is a communication link between this and this, they are communicating with each other. So, when it increases speed, this also increases, when it turns, this also turns, and there are in this slide itself there are many also in this you will have 3 robots, 4 robots, and I just that is no another thing that we have done in formation, we did for ISRO, that you have these micro satellites, right, and you create a formation. So, where they are needed, imagine you have satellites that are tracking Katrina, some tsunami, these kind of events they have to track, right. So, then you see that these storms, when they are spreading, they are not unidirectional, they are all randomly spreading, right. So, one agent cannot really track. So, multiple agents together they will track the flow of the events. Okay. So, this is the application, and we have also in these systems we have applied leader follower, mostly leader follower approach for formation. Just to give you a broader picture, you imagine now suppose we have a smart city, you will see that in Delhi there is a specific group of people who clean the cities, this group of city people known as Balmik, and they do all this menial work to keep the cities clean, but these people are always they suffer from the social stigma. They are looked down upon, they are kind of they live a kind of ostracized life in the society, and so it is important that we actually enable such people with the technology. So, imagine all these dirty things, waste that you have. We just got a proposal from TSDP where we will develop this robot, indigenous robot, and that should be able to do this kind of work, smart waste disposal. That means you have waste, there are organic waste, there are plastics, there are glasses, there are recyclable things, and a robot can automatically separate them and put them in different waste basket, right, and dispose it. So now you have in a city, you can have all these multiple robots together, and they are networked. You can also connect this system to a citizen redressal or complaint system, where any locality can give a complaint here that our locality is not still clean. So, all those things can be done, and this is whole together. You see, there is a control center here from where this teleoperation takes place over the communication network. So, this is a whole thing together we call cyber physical system, right. This is another thing. You see that you have a lane formation. Now recently in the Jamuna Expressway, once I think around 87 vehicles together, they crashed to each other, 87 vehicles, and around 5-6 deaths. That is around 1 month or 1.5 months before. Recently when Hema Malini was returning from Mathura to Delhi, she also met, her cavalcade also is in the middle of such a crash. So, given that we have more bigger infrastructure, and drivers will always make mistake. So, unless we create a driver assistance system, our roads will not be safe. So, this is another way, is that you see these are all vehicles, they must be confined to their own lane, then the distance between D1, D2, D3, D4, D5, they should be always same. So, all those problems can be again solved in terms of a cyber physical intelligent transportation system. Similarly, e-learning portal, we have many experts, but all their expertise can be shared through again cyber physical e-learning portal, where the schools at different parts, they hear simultaneously one speaker, right. So, this is another, and IoT based healthcare, this is also is very important. Every patient's records are there in the internet server. You have smart devices that is connected to the internet, your blood pressure measured here, and that is already connected to your database in somewhere server. The information directly goes there and gets stacked there, right. Whatever your details of you are doing nowadays, all in India is all manual. You go to some pathology, you get your blood tested, your some kind of ultrasonic you might do, all these things, and you get it in a hardware copy. Is not actually, and next time doctor says what has happened to you, neither you know nor doctor knows, because there is no record, right. So, something that can be easily nurtured through this IoT based healthcare. One of my students working on PhD on a smart home. and here the smart heating, ventilation and air conditioning is particularly focusing on this. So, in a smart home, what you want? You want to optimize energy, you want to pay less tariff, right. So, how do you do that? So, there are there are communication protocol, computing protocol and the task scheduling. Like for example, you have a smart meter, the smart meter allows your wash machine to be turned on at exactly a time when your tariff is minimum. Tariff is minimum when less demand is there from the main grid, and tariff is maximum when maximum demand is there or peak demand is there in the load side. So, this is all demand side management. So, a smart home has many other features, I just do not have to go, but this is another aspect of cyber physical system. Okay. Cooperative robotic system, I already told you. This is another thing that we are really interested in working together. We have created with TCS, we are creating a group here with MCRISI. So, where you have multiple such UAVs and they do continuous surveillance of the thing, and then you create an agricultural information system for precision agriculture. The other aspect here is that there are an animal called nilgai that normally eats away 20% of the crop. So, you can always create an automatic patrolling system for saving or driving them away from the crop field. So, this is another aspect, cyber physical energy system, which is becoming a very big issue now, smart grid, and particularly in Denmark, their goal is by 2040, Denmark, 2040 or 2025, I do not know, their entire energy will come from biomass. That means all small units, they are all connected, microgrids, even nanogrids, right, they are all connected together. Okay. And this biomass is going to, and it's amazing that a country like Denmark is ahead in I was seeing one website connected to United Nations, I think UNDP program or something. So, the caption there is think energy, think like Denmark, right, think energy or something, think like Denmark. That means, if you are really want to solve your energy problem, think like Denmark. It is all no risk, biomass, environmentally most healthy, synergetic, and that is what they are doing. So, imagine given that you have many small units, and they are not hundred or thousands, they are millions, they can be millions. Time will come, if you really provide technology, every house will have a unit that is generating some energy. Okay. Otherwise, energy will be so costly in course of time, and I do not have a slide here, but I have a slide in my laptop. The entire fossil fuel and everything that is there according to BP, British Petroleum, all these things will be exhausted in another 150 years, all right. So, energy will be very costly if we simply depend on the fossil fuel. So, those who are smart, they are looking for simple way of generating energy, because we have made our lifestyle so modern, we cannot go back to the ancient ways. We all need energy. So, now how can we self-sustain our requirement? So, now the concept is going, even every household should be ready to fulfill their own energy requirement. We have so much of biomass reject, every household, in terms of vegetable, in terms of your waste of food, you have so much of biomass. If you convert them to bioenergy, you have. So, these are the things people are looking at. I will not go in details. We are actually working on this cyber control of cyber physical energy system. We have a project, 2 of my PhD students are working on this. So, I will stop here as far as I just wanted to give you some idea about cyber physical system. Okay. So, this is topic learning to control visually guided robots, that was supposed to be my topic. So, now I am starting. I will take just another 1 hour is there, right. Okay. We may not be able to cover everything, but we will cover something. So, topics that I will cover is Cohn and Sum, Fuzzy Sum, T.S. Fuzzy based visual control of robot. I may skip adaptive critique because this will be too mathematical. I will go directly to imitation learning, probably we will stop there, maybe little about brainwave controlled robots, right. So, just to give you why intelligent control, you say again the same as I told you, computing, the founding father is von Neumann. In 2000 in the 20th century, that is 1900 to 2000, right. So, that 100 years 100 best book were shortlisted, okay. 100 best books from philosophy to science to everything, right. That really had big impact, the people believed. And in this panel there are journalists, there are scientists, there are philosophers, all big panel of 50 people, and they selected 100 best books, right. One of the book was by John von Neumann, okay. And this book was, the name is The Theory of Self Reproducing Automata, and this is nothing about something has been done, simply a series of thought experiment, okay. And you know that science develops when people know how to do thought experiment, right. Just like suppose all of you are listening, it is time for me to ask some questions, right. So, how do you understand you are different from him? How do you what is that makes a distinction between you and the chair? Say, you see how fundamentally we do not think actually, right. In robotics we try to solve. Can you say two objects, how do you distinguish two objects? Scientifically you have to give an answer science, because we have to do everything in science, right. Two objects, how do you make a distinction? By shape, color, no. Okay, now suppose I am speaking and Professor Madhav Krishna will speak, and there are two audios. When you hear, you make a distinction, yes or no? Yes. So then there is a color there, there is a color, there is a shape. So how do you make a distinction? And first of all, what is an object? What is an object? Because my voice is an object, your voice is an object, right. So what is this object?
So there may be the difference between the approach towards analyzing anything by different persons, like one person is approaching towards
That is, those are all naive ways of speaking. Two objects, the distinction is space. It is space. Space is that gives a distinct identity to an object, right. So space itself is a very scientific concept, okay. Like there is a space, and that space the smell is carried, and that space gives different smell, different form. That is why oh, this is from jasmine, this is from henna. How do you know this? Everything is a special distinction. Okay? So, that is why science starts with the notion of space. If you do not have any idea about the space, you do not understand the abstraction of the space, science does not progress, neither we progress. In fact, the biggest problem in solving this thought experiment of John von Neumann is again spatial complexity. People do not understand the space. Okay? We do not understand the space. Okay? So anyway, what was his idea? Let me give you what is his idea. His idea starts from here. Sorry, his idea starts from here. That is what you are in the first day, as a single cell. Okay? You are there as a single cell there, and imagine this cell has all the information, and from that information, you see, that is evolution, and now you are here. And you are consisting of 8 different form of space. There is not one space, and of course, there is a 9th space. People do not, within science we cannot catch that space, the 9th dimension. There are 8 dimension space in which you are operating, and this all space are coming from the original information that is there in the first cell. So, what Neumann said, that nature is self-replicating. This is all self-replicating, right? Not only we give our self-replication, we will give there is a perpetuation from seed to plant, plant to seed, birds, reptiles, all forms they have self-replication. Nature has it. So, his proposal is, in this book he wrote, can I start with a single memory finite automaton, a small finite automaton with single memory, and allow that machine to grow in terms of hardware as well as software. If I know that, then I understand what is the process of self-replication. Simply speaking about self-replication, in 2003, 2004, the Nobel Prize winner, he got the Nobel Prize to see replication happens. He took a worm, the egg, it became, from egg, it grew from one cell, and this worm has only 261 cell, and that had the procreative organ, the skin, the stomach, everything it has, right? Locomotion, and he understood everything putting inside the microscope. Of course, 261 cell you can easily, you have to sit probably a year, I do not know how many years he sat under the microscope, but he completely diagnosed that, right, and he got Nobel Prize for that, right. We can observe the self-replication that is happening in the nature, but we are not able to recreate it. We are not able to recreate it, but he, through his thought experiment, he said, can we do it? Can we do it? So, this is, but we have not actually gone anywhere near. I will not talk about all these things. You can, those who are interested in something about AI. So, you see that AI in the beginning was basically it became very famous as expert systems, particularly problem solving. These are all problem solver, and you use different logic. We had also those days one software came called Prolog, right. So, first order predicate logic, and then we had reinforcement learning, and of course, simultaneously we had this here the evolution of neural network, the model of neurons starting from McLaupitz's, then Widrow's least mean square algorithm using this perceptron, and then there is Minsky, who appeared to be a very big fellow later, and then another big fellow came there is Paul J. Warburg. He has written a paper in neural networks on the intelligence in the brain, the way forward. I have given my neural network students that paper to digest, and every time I ask questions they are not able to understand, because this is so intelligence, the level of intelligence, and what is intelligence, that is also poorly understood. Those are the issues. What is naturalization of intelligence? These are all philosophy. I will skip all those things, but so Paul J. Warburg started this.
Leaving, I thought I'll ask you a question. So, where do you find deep learning? Where will you fit deep learning here, and what is your take on deep learning?
This is just one approach of deep learning. I don't think that deep learning is doing something big. It is fundamentally it has not changed the way the AI is supposed to go forward. AI or any subject, even including physics, chemistry, biology, will go forward only when we invent the cognitive space. Space is the father, space is the origin. We have no understanding of space. At best, people are talking about the, after Hilbert space, fiber bundles and exotic manifold, something has come, but actually in terms of cognitive space we are very far. Unless the space is understood properly, we cannot talk. It is space finally makes discrimination. It is space that makes you why you are cognitive. Like an ant is less cognitive because he is unaware of the space, or he is ill-equipped with the space, and a human being appears to be more cognitive because he is equipped with higher form of space. So, it is a space. So, when we talk about machines, we are probably working zeroth order space. You go to an insect, probably you are in a first order space.
But generally, the general thing is that these architectures can solve a lot of problems.
No, that is by brute force, that is not by intelligence. Intelligence is not natural there. By brute force, you take 10 layers of neural network and develop an algorithm and feed data. Saying that you are very intelligent is nonsense. But that is what is a deep learning. In a deep learning, the concept is already there. You have already many layers of network, and when we applied backpropagation, they did not work because of vanishing gradient problem. And that is what Hinton solved. He used the idea of restricted Boltzmann machine and made the algorithm very fast. Okay, that means which was converging. Like for example, his original problem was with the handwritten digits. So if you train a neural network, he took 784 in the input layer. That is the number of pixels for representing every character, every digit, and then 1000, 500, and finally 9. This is his network structure. So, if you really simulate it, we found if you apply a backpropagation network, it takes around 16 hours or 24 hours, depending on what kind of algorithm you are running, and you get same accuracy. But what deep learning, the algorithm they developed, it takes an hour, even sometimes less than an hour. That is all. You have reduced the convergence. Now, the point is, you imagine you have a very high level supercomputer like GTU. Okay. So, you can also implement the same thing using backpropagation, even less than 30 minutes, depending on how, suppose you have a very high powered supercomputers, imagine, and dedicate it for this. So, but that is not really an improvement in the knowledge. Improvement in knowledge or space wise, like like why the world was floating or the universe was floating. The came from Newton to Einstein, why again floating, the same question. He brought a different dimension to it. So, that kind of idea, or in the quantum mechanics, where you have two kind of objects, either particle or wave, and you finish those distinctions between wave and particle. So, these are some kind of the original ideas, and we use those ideas in different ways in technology. We have not really gone beyond this. So, deep learning is not really an invention in that way. Yeah. So, when I say here also, I do not think that here we have really made any progress in terms of cognition. That requires, I have actually a proper number of slides to explain that what is called naturalization of intelligence, and you will understand that intelligence in the present framework is never naturalized. Just if you are here 10 minutes, you just wait, I will explain that. So, let us he is talking about whether we have really, Professor Madhav Krishna is asking whether we have really invented a network that is cognitive itself. That is the main question. Okay. You see that what is the fundamental problem in AI? Madhav Krishna, tell me, what is the number one challenging problem? Madhav Krishna is expert in AI and robotics. The fundamental challenge in a robotic as an AI is that you give a machine to read a chapter, like you read a chapter, right? And once you read a chapter, what you do at the end of the chapter, there are questions. You should be able to answer those questions. And with all 1945, the modern AI has come into existence, and this is 2015. So, 55 plus 15 is how much? 70 years. In 70 years of history, we have not been able to solve this simple problem, that as of now our machine cannot read a chapter. Even if it reads a chapter, it cannot answer the questions at the end of the chapter.
Within a very, I do not know in what phase are you, but I am talking in a very normal incremental phase of incremental research that people engage in.
But see here, I just because I'll just you just be 5 minutes, you will recognize why we have not made any progress in true sense of AI. I'll just explain to you. You see, this is a it seems same example you will very much appreciate. You see that this particular system, this is a inverted pendulum. You can model it like this. It looks you use Lagrangian or use motion dynamics, and then you get these equations, right. Once you get these equations, then you can design a controller. In 2002 to 2007, I was holding this control lab for undergraduates in IIT Kanpur, electrical engineering. So, we had an experiment like this. So, what you used to do, we will take this, and this I, M, L, Fc is the friction coefficient. We will take these things from the blueprint, that is the manual of the feedback. The equipment is provided by the feedback company, and then you linearize the system around this equilibrium point, and then design a state feedback controller. This is what we used to give to our kids as students. So, what happens normally, what we observed, suddenly the same algorithm, what is that algorithm? You actually design, because there are 4 states here, theta, theta dot, x, x dot, 4 states are there. And so, when you do a state feedback controller, we have 4 gains, K1, K2, K3, K4. So, you designed it, put it. students will be seeing, array, it is really controlling, and suddenly it will not work. So, my students, and again they will try their best to tune those weights heuristically until it works, and it will fall again, and the next day it will not work. This always happens. Reason why? Reason is, when you really are dependent on the model, you have to have an exact figure for I, you have to exact figure of Fc. Fc is really here varying, because dust will be there, junk will be there, and probably in the motor you may have hysteresis and so many other things which we are not accounting. And as a result, although we depended on this system, on this model, we could not make it work. Now, another approach to control. What Indrani Kar, who did her, and Prem, those who did my PhD with me, what they did, they represented the system like this, and then they linearized the system. We have 4 states. You can say x1 is big, x2 is small, x3 is small, and x4 is medium, like that. You create, and around that, or actually what did they do? They did not say like that. They said x1 is, let us say, your angular position. So, you can say x1 is around 0, x1 is around 15 degree, x1 is around minus 15 degree, xn around minus 30 degree, plus 30 degree, simple, right. And then similarly, your x3 is around 0, around 1 centimeter, around minus 1 centimeter, like that you can linearize the system. Okay. So, that is what they did. They linearized the system around various operating condition, which from the model itself, you do not have to identify the model that is given, you simply linearize it. But what this model, see, this model and this what we saw in the previous page is same thing, but these A's and B's, they are all different linear system matrix and control matrix, okay. And it is very visible, it is not a black box, and there are R number of rules, and this is the overall dynamics. But what is the difference between this and this? This is rigid, whereas this one flexible. This can handle the uncertainties, because here once you put a parameter m, I, f, c, finished, nothing can we do with this model. But here, even if those parameters are uncertain, this model can handle those uncertainties, right. And now you take this model, linearize this model around A x t and B u t, put all other terms here, consider them as a disturbance. You can create a disturbance observer, or like here we have designed a robust controller, right. That means we found the norm bound on this disturbance, norm bound on this disturbance, and based on that you design a controller here, right. And once you design the controller, we plotted this gain, like for example, here you take this system, you linearize this system, the gains are fixed. That means in this space the gain will be only a single point, but here the gain is varying. That is why you say variable gain controller. Your gains are varying as your system is traversing on different trajectories, right. Now you see that after designing this, we have designed at least 3-4 different kind of controller. This particular thing is published in IEEE Transaction SMC. The another is fuzzy sets and systems, and you implement this controller here. So, you see here, this is your mean position, your cards should be always around this mean position, this pendulum has to be always upright, vertically upright, and you see that frame is giving that is disturbance there, and always it comes back to its mean position, and the pendulum is always in vertical position. And you see that when we implement this algorithm, this never fails. This will never fail. Okay. Now, they ask the question, when we implement this, can I say my machine is intelligent? Think about this, Madhav Krishna, then you will understand. Is the machine intelligent? Who is intelligent? The person who did it. Okay, that is to think about such a model and to think about this, who thought? I. That means I as an individual am unaware of my own cognitive ability in terms of cognitive space. Unless that is unraveled, machine cannot be made cognitive. Okay. So, here we designed, we brought this model, we presented this model like this, and then we incorporated the robust control, and then we designed this controller, and this is put into the machine. Okay. And we say controller is intelligent, controller may be intelligent from the perspective of the person who has designed, but machine has not become intelligent. The basic goal of AI is to make machine intelligent. I hope you got the point now. Okay.
This point is small.
Huh?
I mean, I was asking in I think I was trying from the point of view of neural.
No, now you understand that we do not understand our cognitive ability. You understand? So, this is the idea. So, that is when you do not understand that, you cannot make really a machine cognitively empowered. Okay.
Yeah, but yeah, well, there is, but we do have now machines which are able to beat humans, like the Go champion. So
that is not
or
really.
you have chess engines which can do a lot of things.
No, that is all exhaustive search. Those are not intelligent. Still, you are not getting the point.
No, I get the point. Yeah.
Those are all brute force. That's like a deep learning has been used to solve many big problems, but their machine is not intelligence. It's a philosophical issue. Yes.
You are not.
Yeah.
Sir,
Yeah.
I mean 3300, 3400 chasing means they are, I mean, you are saying just like that, there is nothing to do with artificial intelligence.
I just told you. Can't you see that this is all AI? I am just giving you an example. In this example, you are seeing that who is doing it. You are not understanding the first principle that I talked about, the von Neumann. Von Neumann has said, you start with a single automaton, make it grow in terms of both hardware and software. If people are not able to think big, okay, all that we do, we bring out the biggest possible computer, supercomputer, we put a possibly biggest neural network in that, and we try to simulate. This is all nonsense. I have seen people working on neuromorphic research. Okay, all that do is that they bring all this, this what they are called massive VLSI networks, and that they code. There are millions of circuits there, and they try to program everything and want to see, oh, can we actually simulate a brain? But those are actually not addressing what I am asking, the fundamental core principle of AI. Yes. So, you see here,
You miss your flight otherwise. You miss your flight, I think.
Oh no, that got delayed.
okay, so safe journey back to Hyderabad. So, now let us talk about something about the robot visual control. So, you see here this is a 7 degree of freedom robot and there are 2 cameras there. There are also camera here and here. You can place the cameras wherever you like. You can also place a camera on the tip of the end effector, and you see that these joints that you have, there are 7 link, means there are 7 joints, and based on specific angle, the joint vector here, this tip position will occupy a specific position in the task space. So, what we write in the forward kinematics of this robot is x equal to f of theta, where theta is 7 dimensional in this case and x is 6 dimensional if you take orientation into account. If you are not considering orientation, then x will be x y g, 3 dimensional. Now, what you can do, x equal to f theta, you differentiate x with respect to time here and f theta also with respect to time. Then you get this expression x dot dx upon dt is dou f upon dou theta into theta dot. So, this dou f upon dou theta is your Jacobian matrix. So, this gives you the motion in the joint space and motion in the Cartesian space are related by a Jacobian matrix. When this tip is moving here in the task space, there is pixel movement also in the camera. So, that is the motion in the pixel space or image space and motion in the task space x dot is connected by a image Jacobian L. This L is also different for different objects, and that also needs to be estimated in real time. Suppose I want to manipulate this object directly from the image space, then I want to look at the relationship between the motion in the image space and motion in the theta space. So, that becomes like this. And if I select my controller theta dot as this, I can show my dynamics here will be kinematically stable, right. But sometimes the problem with this is that Lj may become ill conditioned because of the singularity and so many other things, and so pseudo inverse may not be always possible. And more than that, when degrees of freedom increases, right, like as I told you earlier that if I this manipulator with our placed in a mobile platform has to play tennis, table tennis, then degrees of freedom increases drastically, and then this may not be real time implementable. That is another issue. So, and then the controller here, you see that this is your desired visual feature and this is the instantaneous visual feature. You set up a error corrector loop, then there is a controller and you do velocity actuation to the manipulator and this controls. So, now this little bit depth I will tell you how we first designed a controller, kinematic controller for this 7 degree of freedom robot manipulator. You see that what we found in the beginning, you see that this workspace, how many points are there? Infinite, right. So, if you really want to learn the model of the robot, kinematic model of the robot learns its own kinematics, right. Then literally you have infinite examples. Now, question comes, how minimally I can select these examples. Then we did a thought experiment. We said, suppose we take only 10 data points for theta 1, 10 data points over theta 2. Randomly I select, theta 1 has certain constraint, let us say 0 to 90 degree, and 0 to 90 degree I randomly select 10 values between 0 to 90 degree. It is possible. Similarly, you select another 10 here, another 10 here, another 10 like that. So we saw that if I select that, the number of data or examples that I have to generate is 10 into 10 into 10 into 10 into 10, 10. So, the 10 to the power 7, that itself is a huge number. If I tell my PhD student, you go and generate such data, it is difficult. So, we ask this question, how many data we can actually generate? Okay. Let us say in 2 hours, how many data we can generate. So, how do you generate the data? You give randomly 1 theta 1, theta 2, theta 3, theta 4, theta 5, theta 7, randomly you generate, and then this tip point goes to some place here, and you observe from the camera where it is. So, that is your one example. In 2 hours, we saw that we could generate around 50,000 data points. We said that using this 50,000 data, only 50,000 data, all right, we will learn the kinematics, and you will see that subsequently whatever I will show you on this all experiment on this 7 degree of freedom manipulator. So, all based on this original data 70,000 data, 50,000 data, and we have designed many controllers, right. And once you have this data, what you do here, the inverse kinematic, forward kinematic is x equal to f theta, inverse kinematic is theta equal to g x. So, when you linearize theta equal to g x, you get something like this using Taylor series, and you create a neural network there 10 by 10 by 10, that is 1000 neurons, and each neuron is associated with one linear model. Why we associate linear model? Because each neuron here represents a small subset of the entire workspace. So, we assume that within that workspace the kinematic is no more nonlinear, it is only linear. Okay? That is the assumption. But because this the robot is redundant, you see that suppose I have to touch my nose, you see, these are all possible kinematic configurations. So, like that you can have infinite kinematic configuration to touch the nose because of the redundancy. That means, you do not have only a single model for the one neuron, you have multiple models. And then there are another issue that comes out. Suppose I am here and I have to reach here, I cannot reach in many ways because this is exterior to my workspace. But when I am near here, I can come from here, I can come from here, I can come from here, so many ways. So, that is, you have to have multiple models for neuron, but the number of these models associated with every neuron has to be learnt in real time. They are not fixed. So, what are the now learning example? I have only 50,000 data points. Using those 50,000 data points, I have to learn what is theta gamma j, what is a gamma j, this is a Jacobian, what is w gamma associated with every neuron, and similarly I have multiple models for each neuron, and number of that models, what is that number, that also I have to learn. So, it is a huge learning problem. Okay. I have to learn this, okay, using this 50,000 data. And so, this particular thing, this is I told you what is the problem, and this is the problem was solved. You see that same target, and robot has many kinematic configuration. That means, for the same when it is coming here, same neuron is the winner. And what you are seeing actually there are 40 such, particularly for this we found out there are 40 models learnt for the same target point. Okay. And then once they are learnt, the robot operates in real time, okay, and it is very fast. And same thing what we did here, the same 50,000 data point you took, instead of learning the inverse kinematic, we learnt using that 50,000 what is forward kinematics using a radial basis function network. Then we ask this question to the radial basis function network, given my target, wherever is the target, the x position, what should be my theta? But when you invert this network, all of you know that given x, how many theta are there? Many thetas. So, which theta it has to select? So, then Swagat, who is now in TCS, he designed a k-sum subclustering network using some kind of a priori intelligence. It generated a hint or an initial guess, and this inversion algorithm for this forward kinematics uses that theta naught and finds a solution around that theta naught, right. And that is how this particular algorithm was developed. So, this you will find in this robotics autonomous system, the previous one you will find in robotica, and sorry. So, this inversion of radial basis function network, you see this is your workspace of the robot, which is cluttered in terms of obstacles. There is a box, there are candles. This experiment Swagat did when I was in Ulster. So, this robot navigates. The two cameras actually back of this robot, two cameras, and then you see that it navigates in this entire workspace without hitting the obstacle, right. Now, the in robot, any you go to any industrial robot, they have put in their PD controller, all manufacturer of industrial robot, they put a PD controller. So, we said that we should also put a PD controller, okay. But because it is a highly nonlinear kinematics and 7 degree of freedom, we will put a distributed PD, multiple PDs. So, PD means you see here proportional gain into error, derivative gain into change in error, all right. And what you have, this is all visual features, you fuzzify them and create a zone, and for every zone you have one PD controller, and then you fuzzy average that, okay. And once you do that, you take a Lyapunov function, find the rate derivative of Lyapunov function. The objective of that, the rate derivative of Lyapunov function is to be negative definite. And how do you make a negative definite? For the details you have to go to the IEEE transaction mechatronics. And then in that process we found out P dot, that the update rule for proportional gain, update rule for derivative gain should be like this, okay. This is all real time, this is adaptive. That means, we are not designing a fixed gain PD controller, adaptive gain PD controller and real time, okay. And if you see that here, So, the camera is there here and looking at the pink ball, and it follows the pink ball, and you see this movement of this entire robot. It is very smooth. So, here robot is being controlled where we are not making use of the robot kinematics, rather we are learning everything in terms of distributed physical PD controller. Okay. So, you saw again, as I am telling you, here machine is not at all cognitive. You can see neither machine decided, machine did not decide this architecture. Okay. Like in this case my PhD student Indrajno, he decided this architecture. Okay. He used some heuristics also, it did not that, it is not that at one go he got this architecture, and then this entire analysis who did? Is doing, machine is not doing. And also this Lyapunov function, machine did not decide, Lyapunov function the researcher decided. This algorithm, proportional gain update and derivative gain update, who decided? The researcher. So, where is machine is intelligent here? Machine is not intelligent. It is the researcher who, based on his own preliminary ideas, his own experience, okay, he is bringing his own experience and he is giving to the order to the data. Okay. And then we saw how this robot is being controlled. I will skip this adaptive critique. How much time I have, Professor Datta? 10 minutes more. So, I will go, I will skip this adaptive critique, this is too mathematical. I will skip all these things now, given only 10 minutes. Okay. I will skip all this, I will start this. I have taught you something, but just to. So, this is something that we are now doing, imitation learning. You make a robot to learn through imitation, right. So, through this robot can learn how to dance, robot can learn how to play tennis, robot can learn how to arrange dining table, study table. Okay. So, these are the things, actually service robots are becoming more popular nowadays. Just to give you some idea what happens actually, this is the whole protocol. Suppose the robot has to learn, this is the dancer, right. So, what dancer is doing, you are observing the dancer through audio, through video, right, through different sensory mechanism. All the dance, suppose the Kathak, let us say this is Kathak. So, in Kathak there are many primitives, bandhan, that means prayer, thought, shalami. So, these are all small sequence of action, and any big action may be sequence of these small actions. That means, a big dance sequence, you must know how to make it small in terms of these small things. This is called movement primitive. Okay, movement primitive 1, 2, 3. And how do you extract this? Through information retrieval. Okay. So, information retrieval itself is a big area. That means, once you have a video of a dancer, right. So, what happens normally when a teacher, this also can you can design an artificial dancer using this concept also, because see, when your dance teacher is in front of you, at that moment you are actually observing and you are learning, right. But what you can do, you can take a video and place the video, and in the off time when teacher is not there, because teacher will not be always there, you can see that video and you can also practice, yes or no. Now, you want that to happen through a robot, how will you do? Now, it is very complicated. First of all, x1, x2, xn, these are all vectors that are extracted from this video. Okay. And these features are converted into different so these features are converted into different movement primitives. Like suppose if you know raga, right. So, raga means it is a sequence of different notes. So, like that you know one has to be very intelligent, it is not that everybody can do it, some expert is necessary to convert these features into these movement primitives. Okay. And once this movement primitives is known, then you synchronize these movement primitives through the joint actuation here, J1 to Jm. This is different sequence. J1 is one moment primitive, J2 is moment primitive 2, Jm is moment primitive m, like that. And then once there are joint actuation, then it will appear the robot is dancing. Is that clear to everybody? This is called moment primitive. So, this is I have already shown you, right, this figure, right. So, this is what just to remind you, and we are doing the same thing now for playing the robot tennis. I think you have made their visit today, right? Today evening, right. So, when you come there, you will see how this experimental platform for making the robot play tennis. So, this I have explained to you, and this is what is Madhav Krishna was telling, the deep learning model for grasping. We have done this, some of the things that here this experiment of grasping. I will just explain to you how this grasping took place. My students collected around 200 synthetic objects from the internet, and then they manually label these objects which is the region of grasping, and once they did it, they put two deep neural network, one is for coarse action, the another is for fine action, and using that they finally, like for example, this is a real object, and my grasper network is able to tell that the neck of the jug is also one grasping area region, as well as the handle is also another grasping area, right. So, like that we are able to make the robot grasp varieties of objects. You will see also after this, it will like this particular bottle also has been grasped. Similarly, you will see now it will grasp this particular object also by neck. We made it to grasp by neck because we did not want our finger to enter inside and get broke. That is why we are grasping this jug by the neck to protect our this hand. This is another concept of programming by demonstration, again same imitation learning. So, you have now this is a pink one, this is another color, this is another color, and robot looks at it, how this was organized, and based on that it goes, and again because this was in the beginning here in the beginning, right. So, it will take this one to there and then put this one on top of this stacking, and you can also make a robot to similar way how to arrange a dining table or a study table. This is the final part. Is the time is there, or I should stop? Okay. So, I will just explain to you another is a brain wave controlled robot. I will not give details of this, this is sufficient here. Okay. This is my PhD student Vaibhav, he worked on this in collaboration. This is actually in University of Ulster. So, you see imagine a person who is sitting on a wheelchair, okay, motor neuron patient, but he wants to have some independence, not all the time a caregiver will take him from here to there or here. Suppose he wants to go there, he should go, right. So, he desires, and that desire is translated into actuation. This is it. So, this is what is happening here. You have a visual feedback, you have a based on visual feedback, the patient decides where he wants to go, right. And then there is EEG, and this motor imagery is collected here, and this is pre-processed, and then there is feature extraction, and then there is some classification based on some binary action, forward, backward, like that, stop or go back, some binary actions. So, those binary actions are made, the patient will think whether left or right, that is all. Thinking is only binary, left thinking, right thinking, left thinking, right thinking, that is all. So, before, that is why before they operate, they are actually trained. All patients are trained in right thinking and left thinking, and their EEG signal is analyzed until the left thinking is exactly left, information will be there in the imagery, motor imagery, right thinking will be in the right, that motor imagery must have that content. So, that training has to be there also. Okay. And then once classification is there, that classification goes to the actuation here. So, this is, you will see, this is called brain wave controlled robot. So, you see these are all binary, halt, forward, left, right, backward, main. So, this is are all, this is all HMI the person has. So, suppose it will ask whenever it is red, that means that is the thinking. You see, sometime it will see there will be some red, you will see, you see the red. So, it is forward, that means it is saying you go forward. So, robot is taking forward step, it was here, it is going forward. So, as long as it is thinking forward, the forward will become red, and then this goes in. And we have made this robot to navigate in this entire workspace, the way the thought pattern goes in, right. So, this is all controlled by EEG. EEG is deciphered, and then the robot goes in. So, this is end. Thank you. Just to make a conclusion, what we did today, I showed you that we started with 50,000 data for the robot, and we made the robot to work in so many ways, right. So, that is, soft computing approaches are all data driven. Learning the model from data is a scientific art, it is not a science in itself. Why it is scientific art? The researcher is doing everything, machine is not doing anything. Okay, that is why it is an art, it is not a science. So, that is the point I was trying to impress. Learning works as different robotic systems are controlled in real time as presented in this lecture. However, what John von Neumann said, emergence and self organizations are big challenges that soft computing approaches are confronted with. That means, if you go back to the same problem, we are not still with single finite automaton that will grow in terms of hardware, grow in terms of software. We are not in that. The reason is that we understand ourselves very little. Okay? That is the main reason. Thank you.